Okay, children, in the last class, we had discussed about the developments leading to the Bohr model of an atom, right? And we had discussed about the dual character, especially the wave nature of electromagnetic radiations, right? So before entering into this electromagnetic radiations, can you tell me which are the two major developments leading to Bohr's model of an atom? Gaia, two major developments that leading to Bohr's model of an atom. Can you tell me?
The electromagnetic radiation possesses two properties.
Yeah.
That is particle-like and wave-like.
Particle nature and wave nature. That's the dual character of electromagnetic radiation. Then one more point.
Experimental results regarding atomic spectra.
Yes, experimental results regarding atomic spectra, right? Then Thomson, can you tell me the drawbacks of Rutherford's atom model?
He did not he did not mention about the stability of an atom.
Very good. Then two more points there. Okay, Devi Krishna, can you tell me one drawback?
Could not explain the line spectra or hydrogen atom.
Yes, yes. Then Aditya Dev, one more there.
Could not explain the structure of atom.
Yeah, electronic structure of an atom, right? Okay, then what do you mean by this electromagnetic radiation? Mahreen, can you tell me electromagnetic radiation?
Yes, ma'am. When electrically charged particles moves under acceleration, alternating electric and magnetic fields are produced and transmitted, and these fields are known as electromagnetic radiation.
They are transmitted in the form of waves, and they are known as electromagnetic waves or electromagnetic radiation, right? Then we had discussed about the properties of this electromagnetic radiation. Then I will show one electromagnetic spectrum. Okay, the electromagnetic spectrum, it consists of different electromagnetic radiations which are arranged in the increasing order of wavelength or the decreasing order of their frequencies. And I just mentioned about the first two electromagnetic radiations, right? This first one, gamma ray. Okay, gamma ray. Here it is arranged in the increasing order of wavelength. So this gamma ray, it has the least wavelength. Okay, gamma ray. Next one, it is X-ray. Second one is X-ray. Then the third one is UV ray. Third one is UV ray. Then the fourth one, that is visible light. Visible light. After this visible light, IR ray. IR ray. Okay, IR ray. Then microwave rays. IR, what's the full form of IR?
Infrared.
Very good. It's infrared. What about UV? UV.
Ultraviolet.
Ultraviolet. So gamma ray, after that X-ray, UV ray, visible light, IR ray, microwave. Then the last one is radio wave. Okay, radio wave. Gamma ray, then X-ray, UV ray, visible ray, IR ray, microwave, and radio wave. These are the different electromagnetic radiations in the electromagnetic spectrum. So this electromagnetic spectrum, it consists of different electromagnetic radiations. They are arranged in the increasing order of their wavelength or decreasing order of their frequency. Okay. And here this values, it shows the wavelength. And here this one shows the frequency. Okay. And you can see that this wavelength is increasing from gamma ray to this radio waves, right? It is starting from 10 raised to minus 16 and ends in 10 raised to 8. And in the case of frequency, it is in the decreasing order. It starts from 10 raised to 24 and ends in 10 raised to 0. So we can arrange it either in the increasing order of their wavelength or decreasing order of frequency. And this visible spectrum, it's in the range 400 to 700 nanometer. 400 to 700 nanometer. That's the wavelength. You have to just note down the wavelength of this visible ray or visible light. This is clear, children? Have you completed this one? All of you?
Yes, ma'am.
Rose, can you tell me which are the different electromagnetic radiations in electromagnetic spectrum?
X-rays, R-rays,
Gamma, it's gamma ray.
gamma rays, X-rays,
Mm.
UV rays,
Okay.
then visible light, increasing IR rays, then microwave rays, radio wave.
Yes, these are the different electromagnetic radiations in the electromagnetic spectrum. They are arranged in the increasing order of their wavelength or decreasing order of their frequencies. This is clear, children? Yes, right? Then we are going to learn about certain parameters that are used to represent these radiations. Okay, we have learned certain terms here, right? Wavelength, frequency. Along with this wavelength frequency, we are going to learn wave number. Okay, I think you already know. First one, you have to write wavelength. Write down the heading characteristics of a wave. So we can express the characteristics of a wave in certain parameters. First one, it is wavelength. Wavelength. It is represented as lambda. Okay, lambda. Wavelength can be defined as the distance between two successive crests or troughs of a wave. I told you, when you draw a wave, this portion, it is known as crest. Okay, crest. Then these two portions are known as trough. So the distance between two successive or adjacent crests, it is known as wavelength. Or either the distance between two adjacent troughs. Okay, successive crest or successive trough of a wave. That is calculated as wavelength. Wavelength can be defined as the distance between two successive crest or trough of a wave. And it is measured in the direction of the wave. And wavelength can be represented by the Greek letter lambda. It is pronounced as lambda, the symbol lambda. And we can also measure this wavelength in meters, centimeters, nanometers, etc. Okay, we can measure this wavelength in terms of meters, centimeters, nanometers, etc. And this 1 meter, that is equal to 10 raised to 9 nanometer. Okay, 1 meter, that is equal to 10 raised to 9 nanometer. So wavelength can be defined as the distance between two successive crest or trough that is measured in the direction of the propagation of this wave, and it is represented by the Greek letter lambda. Then the units used for representing this wavelength, it is meter, nanometer, centimeter, etc. 1 meter, that is equal to 10 raised to 9 nanometer. This is clear, children? Is it clear? Have you finished? Shall I move to next one?
Yes, ma'am.
Yes. So the next one is frequency. Second parameter that used to characterize a wave, it is frequency. Wave frequency, it is the number of waves that pass a fixed point in a given amount of time. The number of waves that pass a fixed point in a given amount of time. And the SI unit for this wave frequency, it is hertz. Okay, it is hertz. Where 1 hertz equals 1 wave passing a fixed point in 1 second. Okay, and a higher frequency wave has more energy than a lower frequency wave with the same amplitude. You need to write these 2 points, first and second one. Wave frequency, it is the number of waves that pass a fixed point in a given amount of time. And the SI unit for wave frequency, it is hertz. In short, we will write H then Z, hertz. Okay. Meryl, can you please read the slide? First 2 points.
Wave frequency is the number of waves that pass a fixed point in a given amount of time.
Okay.
SI unit for wave frequency is hertz, where 1 hertz equals 1 wave passing a fixed point in 1 second.
Okay. Then can you tell me the value of speed of light? Speed of light.
3.2 something.
Yeah, 3 into 10
And
raised to
3.
8. Very good. Okay, it's a constant value. You have to remember this one. Velocity of light or speed of light, it is always 3 into 10 raised to 8. You have to note down this one. Okay. Speed or velocity of light. It is always represented as Z with the symbol Z. Okay, C. 3 into 10 raised to 8 meter per second. That's the value. 3 into 10 raised to 8 meter per second. Again, there is one equation related with this velocity of light, then frequency and wavelength. That is equal to Z equal to nu lambda. What is this nu? Nu stands for frequency.
Wavelength.
Lambda stands for wavelength. Okay, nu stands for frequency. And this lambda stands for wavelength. And C, it is the velocity of light. It's always a constant and its value is 3 into 10 raised to 8 meter per second. C equal to nu lambda. Okay, speed or velocity of light, that is Z. Its value is 3 into 10 raised to 8 meter per second. Then C equal to nu lambda. That's equation relate frequency, wavelength, and velocity of light. Have you finished? Adulya, can you tell me? Yeah, any doubt, children? No. Okay, Adulya, can you tell me the relation between this frequency, wavelength, and velocity of light?
Velocity of light equal to mu lambda frequency into wavelength.
Okay, C equal to nu lambda. Nu stands for frequency and lambda stands for wavelength and this Z stands for velocity of light. Okay. Shall I move to next one? That is wave number.
Yes.
Yes. Okay, one more point. In the previous slide, you can write here it is nu. Okay. Frequency, it is represented as nu. Nu. Yes. The next one is wave number. Wavelength, it is defined as the number of wavelengths. Sorry, some mistake here. It is wave number. Okay. Wave number. Just wait, children. Yeah. Instead, you can write here wave number. This is defined as the number of wavelengths per unit length. Wave number, it is defined as the number of wavelengths per unit length. The wave number, it is simply the reciprocal of wavelength. Okay, it is the reciprocal of wavelength. That means 1 by lambda. Wave number is equal to 1 by lambda. That can be represented as nu bar. Okay, it is represented as nu bar. Wave number, it is defined as the number of wavelengths per unit length. The wave number is simply the reciprocal of the wavelength. That is 1 by lambda. Nu bar is equal to 1 by lambda. When the units or units of this wave number, it is 1 by m. Otherwise, we can write m raised to -1 or centimeter raised to -1 or millimeter raised to -1. Okay, it is 1 by lambda. This meter, centimeter, millimeter, etc. we are using as a unit of this wavelength. So we can write the inverse. That's a unit for this wave number. Wave number, it is defined as the number of wavelengths per unit length. That is simply the reciprocal of wavelength. That is 1 by lambda. And wave number can be represented as the symbol nu bar. Okay, nu bar. Unit, meter inverse, centimeter inverse, millimeter inverse, etc. The SI unit is always meter inverse. Okay. This is clear, children. Any doubt? Anyone? Finished?
Yes, ma'am.
Yes. Lakshmi, can you tell me which are the parameters that we are used to characterize a wave?
Wavelength,
Yeah,
frequency, and wave number.
wave number. Okay. Pooja, what's the symbol of wavelength?
Lambda.
Yes, it's lambda. Then G, what's the symbol of frequency?
Nu.
Yeah, it's nu. Then Jewel, what's the symbol of wave number? Yeah. Wave number. Symbol of wave number?
1 by distance.
That's equation. How can we represent this one wave number?
1 by lambda.
It's equation, right? Nu bar. Okay, it's nu bar. Then how can we define this wavelength? Sarah, how can we define this wavelength? Wavelength. It's distance between?
Distance between a crust or a trough.
Yes, successive crust or successive trough. Okay, then what about frequency? Abhinav, what about frequency? Abhinav, can you hear me?
Yes, ma'am. Yes.
Yes. How can we
Ma'am,
define frequency?
ma'am, wave frequency is the number of waves that pass a fixed point in a given amount of time.
Okay. Then what about the unit of frequency? John Philip, unit of frequency?
Hertz.
Hertz. Okay. Then Shabarinath,
Yes, ma'am.
what about the unit of wave number? Wave
The
number.
reciprocal of meter raised to minus 1.
Yes, m raised to -1, then centimeter raised to -1. That's it. Okay, then one more question. What about the value of velocity of light? Fahis? Fahis, all of you please switch on your videos. Fahis, are you there? Rahul, can you tell me?
Ma'am, 3 into 10 raised to 8 ms.
Meter per second. Okay. Okay, then we are moving to the next topic. That's the drawbacks of this wave nature of electromagnetic radiations. We have only learned about this wave nature of electromagnetic radiation, right? I told you there are dual character for this electromagnetic radiations. We have only learned about the wave nature of electromagnetic radiations. And this wave nature of electromagnetic radiations cannot able to explain following phenomena. Okay, first one, black body radiation. Second one, photoelectric effect. Third one, heat capacity of solids as a function of temperature. And the fourth one, line spectra of atoms. We will learn each topic, each phenomenon in detail. Okay. The drawbacks of the wave nature of electromagnetic radiations. Okay. So these phenomena cannot be explained with the help of this wave nature of electromagnetic radiations. That's why that leads to the developments or the discoveries leading to this particle nature of electromagnetic radiations. Not all phenomena of this electromagnetic radiations cannot be explained using this wave nature. That's why later they formulated this particle nature or the dual behavior of this electromagnetic radiations. Emmeline, can you read the drawbacks of wave nature of electromagnetic radiation?
Black body radiation, electric effects, capacity of solid as function of temperature,
Yes.
line spectra of atom.
Yes. And two phenomena can be explained using this electromagnetic radiations. You can also point out these two. Merits of wave nature of electromagnetic radiations. First one, it is able to explain diffraction. Okay, using this wave nature, they can able to explain diffraction. And the next one is interference. That's related to the wave nature of electromagnetic radiation. Diffraction and interference. This is clear. Navarine, can you please read the slide? Both drawbacks and merits of this wave nature of electromagnetic radiation.
Yes, ma'am.
Yes.
Drawbacks of wave nature of electromagnetic radiations. First one, black body radiation. Second, photoelectric effect. Third, heat capacity of solids as a function of temperature. Fourth, line spectra of atoms. Now, Merits of wave nature of electromagnetic radiations. First one, diffraction. Second, interference.
Okay. Have you completed, children?
Yes.
Yes. The next one, black body radiation. So it can be explained with particle nature of electromagnetic radiation. Okay. It can be only explained with the help of particle nature of electromagnetic radiations. Black body radiation. First, we can learn what is mean by this black body. Okay. An object that absorbs all radiation falling on it at different wavelength. That means at all wavelength, it is called a black body. Okay, an object that absorbs all radiations on it at all wavelength, it is called a black body. We know that this black color will absorb almost every radiations, right? That's why we feel very hot while wearing this black clothes during summer season, right? So here this black body, it's an object that can able to absorb all radiations falling on it at all wavelength. We have learned different electromagnetic radiations based on different wavelength, right? Gamma ray, X-ray, UV ray, visible ray, infrared ray, microwave ray, radio waves, right? So this object that absorbs all types of radiations falling on it at all wavelengths, it is called a black body. And next one is black body radiation. When a black body is at a uniform temperature, its emission has a characteristic frequency distribution that depends upon the temperature. Its emission is called black body radiation. Along with the absorption of this all radiations with all frequencies, it can able to emit certain radiations. That's known as black body radiation. When a black body is at a uniform temperature, okay, that means same temperature everywhere in that black body, its emission has a characteristic frequency distribution. That means it will emit a radiation with a characteristic frequency. On such temperature, its emission is called black body radiation. Or either we can define it as an ideal body which emits and absorbs radiations of all frequencies uniformly. It is called a black body, and the radiation emitted by such a body is called black body radiation. You can choose either definitions for this black body and black body radiation. An ideal body which emits and absorbs radiations of all frequencies uniformly. It is called a black body, and the radiation emitted by such a body is called black body radiation. After this, I will show you one example of this black body. Niranjan, can you please read the slide?
Yes, ma'am. Particle nature of electromagnetic radiation. Black body radiation. Black body, an object that absorbs all radiation falling on it at all wavelengths, is called a black body. Black body radiation. When a black body is at a uniform temperature, its emission has a characteristic frequency distribution that depends on the temperature. Its emission is called black body radiation. Or an ideal body which emits and absorbs all radiations of all frequencies uniformly is called a black body, and the radiation emitted by such a body is called black body radiation.
Okay, this is clear, children. Adulya, is it finished?
Yes, ma'am.
Yes, okay. Then this is an example for a black body. Okay, this carbon black approximately closely to black body. A good physical approximation to a black body is a cavity with a tiny hole which has no other opening. Okay, you have to consider a cavity with a tiny hole which has no other opening. Any ray entering the hole will be reflected by the cavity walls and will be eventually absorbed by the walls. So such a cavity can be considered as a black body. A black body is also a perfect radiator of radiant energy. So you have to consider a good physical approximation to a black body is a cavity with a tiny hole. Okay, it's a cavity with a tiny hole and no other openings. Any ray entering the hole will be automatically reflected on the walls of that cavity and will be eventually absorbed by the walls. Okay, such a body is considered as a black body. Only need to write this much. Okay, and a black body is also a perfect radiator of radiant energy. It will radiate radiation, that's it. So along with this radiations, they can able to emit certain energy. It is known as radiant energy. And Mary, can you please read the example for a black body? Yes. We can't hear you. All of you, please switch on your videos. Devika, can you please read?
Yes, ma'am. Carbon black approximates fairly closely to black body. A good physical approximation to a black body is a cavity with a tiny hole which has no other opening. Any ray entering the hole will be reflected by the cavity walls and will be eventually absorbed by the walls. A black body is also a perfect radiator of radiant energy.
Yeah. Have you completed, children?
No, ma'am.
Okay, okay. Then you can write it. Finished?
Yes, ma'am.
All of you? Okay, then two more points you have to note along with this black body radiation. So this amount of light emitted, you can write amount of light emitted will be depend upon the temperature. Along with that amount of light emitter and the spectra and the spectrum stored will be depend upon temperature. Okay. Temperature. Then at a given temperature, the intensity of radiation emitted increases with increase in wavelength. Increase in wavelength. It reaches a maximum value and then reduces. And then decreases. Have you completed, children, these 2 points?
Yes.
Yes, right? Okay, then this particle nature, wave nature of this electromagnetic radiation, it could not explain this phenomenon with the characteristic or the parameter that is related to intensity. Okay, later one more theory came, that is Planck's quantum theory. Okay, Planck's quantum theory that we can discuss in the next class. Okay, Planck's quantum theory. Before winding up, can you tell me how many of you can able to take seminar from this first chapter? Yeah. Yes.
Ma'am.
Yeah. Aditya Dev, you are ready. Okay. Then 4 more. Who is that?
Ma'am.
Abhinav.
Ma'am.
Yes, Aditya Dev.
First chapter, no, basic concepts.
Sorry, second chapter, not first one, second. Aditya Dev, Abhinav, then 3 more. Yeah. Yes, children, please respond. I need 3. It's not a big task.
Ma'am,
Who's that? Meherin. Okay, then one more.
Ma'am, Samia.
Samia. Then one more. One more chance.
Ma'am, me.
Yes. Sarah. Yes, very good. So you can select any topic from the second chapter. Okay. And just inform me which topic you are selecting. You can take any topic from the second chapter. Then you can present it in PowerPoint mode as you wish. Okay. Okay, children.
Okay.
Yes. You can look at if it is completed portion or uncompleted one, no issues there. Okay. You can also select upcoming portions from this chapter. If it is possible, you can take it. We can start it from the next week onwards. Okay. Yes. So what all things we learned today? Do you remember the topics? You can just go through the slides and recall the points. Just 1 minute. Yes, starting from isotopes, right? Isotopes, same element with same atomic number, different mass number. The next one, isobars with different atomic number, same mass number. Then we learned the drawbacks of Rutherford's atomic model, could not explain the stability of an atom, then did not explain the electronic structure, then could not explain the line spectrum of hydrogen. Then two major developments that is leading to Bohr's model of an atom, that is the dual character of electromagnetic radiation. That means wave nature and particle nature. Then the experimental results regarding atomic spectra. Then we learned the wave nature of electromagnetic radiation. James Maxwell was the first to give explanation about the interaction between the charged bodies and the behavior of electrical and magnetical field. Then we learned about electromagnetic waves or electromagnetic radiations, different properties of this electromagnetic radiations. Then we learned about electromagnetic spectrum. It consists of all electromagnetic radiations, different electromagnetic radiations involved in the spectrum: gamma ray, X-ray, UV ray, visible ray, infrared ray, microwave, radio wave. Then we learned about certain parameters that used to characterize a wave, that is wavelength lambda, then frequency nu, wave number nu bar. Then the drawbacks of this wave nature of electromagnetic radiation and the merits of wave nature of electromagnetic radiation. Then we learned about black body radiations. This is clear, children? If you have any doubt, you can either ask me in the class or in the WhatsApp. Okay, no issues there. Okay, so all of you read this portion very well before the next class. Okay, children? Then let me take your attendance. Just wait. Okay, thank you, children. See you in the next class.
Thank you, ma'am.
Thank you, ma'am.
Thank you.